GISC 2023의 전체적인 의미와 목적을 전달하는 기조연설을 청해 듣도록 하겠습니다. A System Perspective on ICT Standardization 이라는 주제인데요. ISO, IEC JTC1, SC 40일 의장이신 프랑스와 코알리에 의장님께서 기조연설을 해주시겠습니다. First and foremost, we have the chair of ISO IEC JTC1 SC41, Professor François Coallier for the keynote speech. 여러분, 의장님을 무대 위로 모시도록 하겠습니다. 큰 박수로 환영해 주시면 감사하겠습니다.
Thank you very much. It's an honor, a pleasure for me to be in Korea again, to enjoy Korean hospitality, and also to have the honor and pleasure to talk to you at this conference. The topic, as I mentioned, is about the system perspective on ICT standardization. What I will do, and my apologies, I do have to wear these to see better. So I will, in the next 40 minutes, do a walkthrough and general introduction from a certain perspective on information and digital technology, and starting with the concept of the Internet of Things, talk about the new ubiquity we have with IT, about can we trust those systems, talk about the biodigital convergence, and then conclude. So the key point of this presentation is that in the last 20 years, ICT has changed a lot. The market around ICT has changed, and a lot of new technology services have been enabled by ICT, and it is still changing. So what we will do is explore together, taking as a starting point the concept of the IoT, Internet of Things, or again, it has an impact on standardization, and we'll conclude on this. So, talking standardization, ICT standardization started quite a while ago, but in 1987, the ISO and the IEC decided to consolidate work and standardization work in this area and created a joint technical committee. In those days, the principal and most important stakeholder, customer of ICT standardization was the IT industry. So what is IT? And it's again a term of reference of this joint technical committee or around this. We're talking about essentially resource used to acquire, process, store, and disseminate information. Information being data in a context, data being, again, from an IT, pure IT point of view. Telecom people define it a bit differently, but it's, again, the raw data, the raw that is coming out of sensors or may come out of other devices. In the last 36 years, there's been a lot of change in IT. The main engine was miniaturization, Moore's Law. Tied up to this was also economical change in the sense that not only we had denser circuit, but the impact was change. It's not only Moore's Law, but you had also more sophisticated computing circuit, more sophistication in IT technology, and also it did enable a lot of other change in our technological world. I'm putting there the example of my apologies, of a Apple chip, but the system on the chip is illustrate all those different change. Initially, you had very dumb CPU. I remember my first PC, even the floating point unit was a separate chip. Now you have also GPUs, different architecture that developed through time, vector-based, and you have also neural processing unit that are miniaturized and you can find in different also things, and other specialized circuit that you integrate together. So more change in sophistication in architecture, and it is still not finished. So as I mentioned, this cheap computing power was an enabler for scientific development. I'll talk later about biodigital convergence as an example. So it enabled technical progress not only in IT, but in a lot of non-IT related fields. And also, I don't know if some of you remember, in the 1990s, talking about artificial intelligence was like talking about science fiction. And it was also a bit negative when you view all those people making research in computer science in those areas. It was viewed like walking 6 feet in the air in the cloud. And it changed suddenly in the last 20 years, and even more suddenly earlier this year with ChatGPT. So all of that was made possible by, again, this impact of Moore's law, as we say. And IT. IT was already ubiquitous in a certain way when the year 2000 bug came in. They were referenced to embedded IT, but nowadays it's much more different, much more ubiquitous, and will get even more with all those smart environments that are being deployed. Tied up to, again, associated to IT, but it's not proper to IT. It's a lot of different other domains see that, is the hype cycle. New technology coming out, a lot of overselling of the technology, some very enthusiastic and also very optimistic. Again, opinion may come out, and there's some financial also interest tied up to that, new ventures, and then reality may hit. Some of those technology may take a lot of time to realize their potential because you need some other component of the ecosystem. Some may never come with their potentials, and some, when they realize the potential, may have a big impact, maybe even disruptive. I can make the parallel outside of IT with fusion technology. 40 years ago, we were told in 20 years we'll have fusion energy cheap. And nowadays, they say 5 or 10 years. I hope it will come. It doesn't mean it's bad. It doesn't mean that it's simply sometimes you have some very hard and difficult engineering challenge that you need to resolve. And hopefully quantum computing won't come into this category. So a lot of different IT technologies, some of them being a mashup of different coming out and proceeding through this hype cycle and deploying. Now back to standardization in this context. GTC1 through time evolved, some subcommittee were created, working group merged into subcommittee, and it's still covering a lot of traditional technology as well, some very new one. And you can map those technologies. It's a personal view that has been published in GTC1 without too much feedback. But again, you can make abstraction of all those numbers you see of committee. It's simply to illustrate that it's all over the place. Some emerging technology. Working group 14 is quantum computing, SC43 brain-machine interface, and some other technology that are more mature, but you still need to do to support the standards, support the market. So let's talk about the Internet of Things, and you will see why it is a good starting point to talk about this topic. Because the Internet of Things is not a technology. You can see the definition there, talking about an infrastructure of interconnected entities that also process and interact from information from the physical and virtual world. So it's a system concept, the IoT, that use many technologies. So not a technology by itself. We'll talk more about that. But we're talking about systems that are, again, data-intensive, network-centric. Internet doesn't mean, as you all know, the internet. It simply means network it. And also, we're talking about systems that use distributed computing, and some of those systems, I'll give an example, are cyber-physical. But the key thing is that IoT systems are the enabler of some people we call smart everything. Now, it's a market that's evolving very fast. These statistics I took from a reference that's there. Are pure IoT object. You don't have in there all the smartphones and other objects, and you don't have also RFID chips and things like that. So what you can see there is that there's a growth, a very fast growth in the number of interconnected objects in the world, and you can see also that they're using a lot of different networking communication technologies, each of them having their own economics and also technical characteristic. In my home, I have object interconnected by Wi-Fi, by Zigbee, and by LoRaWAN. So it's all different mix, different applications. And I have, again, part of my domotics is through the internet, fiber optic link, and I have another part, you can guess a security one, that's through a cellular network. Distributed computing. Distributed computing doesn't mean only cloud computing. We're talking about, for many type of application, the need to do the processing close to the data source. So edge computing and the concept of fog nodes also. And also the things are smart. Even sensor nowadays have onboard processing, and they can do a lot of things. And then you have smart objects. And at each of those layers, you'll have different type of interconnection, different type of technology that are used for networking. Now, moving close to the source of data is not only because of the large amount of data, it's because also sometimes you need to have more resilient infrastructure. There may be other requirements, and this is one of the engineering solution to do that. So not only cloud computing. Sensors. Sensors, I mean, the art of any IoT system. In IoT system, a good deal of the data come from sensor, and then it can be mixed with other type of data. A lot of things can be measured with sensors. A lot of different technology can be used to measure it with its own impact and its own characteristics. And a lot of different application. What I'm showing there is, again, a paper about one type of sensors using, again, instrumenting humans. Sensors are standardized because sensors, again, the physics is different at the sensing part. The interface may be standard. So there are a lot of IOC committees standardizing different type of sensors, mostly in the IEC. It's not done by a C41. It's only a part, again, of an IoT system. Which come back to data. Data-driven environment. This is what you have. Data. Raw data coming out of the sensor. The raw data must be put in a context, and then it must be analyzed to be able to extract value out of this data. So we have a lot of sensor data coming into the mix. Traditional mix in 1987 was mostly business data, with some exception in the aerospace and other specialized area. So smart everything, everywhere, this is what IoT is enabling. But where is the smartness coming? So simply to illustrate, this is coming out of a consortium working on smart farming, and you have a traditional framework, very traditional, the things at the bottom and the analysis at the top. And this is what I want to stress there is, again, in those smart systems, you have a lot of data processing, and that you may use a lot of technology. And you have, in many cases, big data, a lot of velocity, a lot of variety, and you may use AI technologies, because as you know, AI is a family of technologies, and digital twins. So an example, again, idealize, if we want to move toward more personalized medicine, being able to have real data from a human and look at the history and look at and have a system, again, a learning system that has learned a lot from not only history, but also a knowledge base, and out of that, we can make prediction. We can make personalized, give personalized medical treatment, but also be able to find out in advance when if something is bad and do some preventive, again, medicine. Like you can do that with machines. In smart manufacturing, in aerospace, it's called, again, preventive maintenance. Digital twin is one step higher. Digital twin will aggregate, again, data representation and also analysis, but it's pushing things a bit further because it's also include a model of the real world. And this model, I should say, is more a series of models that are embedded, which mean that you can do what-if simulation and production. And it's a concept, you have an example there for, again, a greenhouse can be applied across a lot of discipline. This is, again, for a ship. And you can see different type of models, different type of modeling techniques, including rule-based, again, that can be used. Actuators, we're talking about enacting, changing the real world. These are the world of actuators. Actuators that can be controlled by human or by machine. And again, when they're controlled by machine, we're talking again about depending of what you change in the real world. If there are humans around, then safety issue come into play. Now, an autonomous vehicle is an IoT cyber-physical system. So you have sensor, actuator controlled by a machine. All of that embedded inside a car. So IoT concept can be found everywhere. And which brings us to another strategic consideration, the convergence of what we call IT and OT. Operational technology are all the systems that are used to monitor event process in industrial production, building, etc. And in the past, we had two solitudes. And we could see that in standardization. We could see that also in the market, different companies. There was the OT world, industrial engineers, own protocols, ardent system, etc. And then you had the IT world where concepts like availability, reliability, resilience were not necessarily present for any application. And what we saw in the last 20 years is a convergence of those two worlds. Again, the IT world is mostly JTC1 that I talk about, and the OT world, industrial control, is the IEC and the IEC JTC1. So what we have is a convergence that brings what was called the industrial Internet of Things. I talk about all the good side that technology can bring, a smarter environment, more efficient environment. There's a lot of potential, but there's also the other side of the coin. So the other side of the coin is that we're deploying more complex systems, increased complexity, more software. And the question is, can we trust those systems, especially if they are connected to the internet, which is not necessarily a good idea for some application. So you know the internet is a very dangerous place. Those of you that do security, the moment you expose a server in a DMZ to the internet, it is scanned automatically by robots to see if there are vulnerability. In some places, it may be more vulnerable than others. I work now for the last 20 years in university, and there are campaigns to try to penetrate a network on a regular basis, very tailored. What's of interest probably of those people trying that is to have access to some R&D labs where there are some industrial R&D projects. So in the world, an IoT world, it can be even more dangerous. This is a very classical test that was done quite a while ago and demonstrated that with malicious code, you could destroy a diesel generator that was widely used. And I won't pass the video, but it was, again, very convincing, the test. Not everybody can do it, and there have been other cases like that. You embed IT, you make have smarter environment, like a smart grid, etc. You're also having more vulnerability and more complexity. So again, the challenge is, can stakeholders trust all those IT-intensive systems? We want to have trustworthy system. I'm talking as a system engineer, trustworthy application. What do we mean by trustworthiness? This is a very high-level definition, meeting stakeholder expectation, not requirements. Requirements are derived. It's an engineering exercise and are derived from the expectation, the stakeholder expectation. And to do that in a way that's verifiable. If it's not verifiable, how can we trust? It's not easy. Now, when we have an high-level attribute like that, what we do have, we can decompose it in a lot of sub-attributes or characteristics. And you can see the list there. Authenticity, accuracy, accountability, and I can go on. You have the usual security, quality, you have safety that we talk about, and then resilience, robustness, transparency. So again, there's overlaps between those different views. When you have complex system, you need a lot of different views to describe it. You will need a lot of, these are what we call those type of attributes that are non-functional. You need more than one to be able to describe your requirements. And what's special about this definition of trustworthiness compared to, for instance, the concept of dependability that came out in the 90s is the amount of attributes that are directly or indirectly tied up to data. Data is important in our world, much more than it was, again, previously, and data coming from a lot of different sources, human-generated and sensor data. And why is it important? I think everybody that studied IT, this is a saying from the 1970s, garbage in, garbage out, GIGO. Take a nice learning expert system and train it with data that is corrupted, and you'll have a corrupted AI system. And you can apply that to anything. You want to base your decision on data coming from sensors, but sensors are not perfect. They can have calibration problem, they can age and start having drift, there can be some interference coming in the communication, etc. You need to be able, this data must be clean, they must be meted to have some kind of resilience at the data level. So there's a whole large body of knowledge in data governance and data management. And this body of knowledge that's traditional apply to this system. It has to be applied. And there are standards that exist on data quality. So those standards are existing and have been published, some of them for quite a while, because it's not new as a concept. The problem, again, is the application. Now, I mentioned, again, for AI, Subcommittee 42 of GTC1 is currently working at a whole series of standard on data quality for AI system, the garbage in, garbage out issue that's coming in. Another attribute that I want to draw your attention on is resilience. We're talking about embedding IT, complex systems that are in our society, transportation, car, cities, etc. We need to use that IT to increase the resilience of those systems. Systems that are what we call socio-technical with humans are inherently, if again it's well organized, or humans are well organized, very resilient. You want to have a system that use IT automation to be resilient. Resilient means being able to resist, having the robustness to a disruptive event. It means also normally a graceful degradation. You don't have a change of state. It's working and it's not working. You may have in complex systems some function that may be shut down first before others, like in a submarine. The last thing that will go out probably will be the system that keeps the crew alive. So, and these things must be engineered. They must be thought about. And again, tied up to that is still the concept of availability and et cetera. So building resilient system is a system engineering discipline. There's a lot, again, there's a body of knowledge. It's not something simple. And it's not, you may have general concept, and after that, you need to apply it to your application domain. Are they trustworthiness standard? They are. What I put there is only those where the word trustworthiness appear at the eye level, and you can see the vocabulary that came out. Vocabulary may seem mundane, but if we cannot communicate, if we cannot specify, and we cannot work on the problem. So it's always the starting point. And it's not because I was the editor of this document that I mentioned that. And there are others that are work, and then there are other standards that are address some specific attributes, again. But as you know, talk about standard, but you know standards are a piece of paper, a PDF document. A standard are worthless if they're not put in use. And they can be invoked by regulation, but they have to be invoked. To start with, a standard is only a document. Now, how can we assess trustworthiness? Again, a personal view, but the first thing, if I had to look at it myself, will be first doing the right thing. I mean, we're talking about meeting expectations of stakeholders. So are we meeting those expectations? Is it well validated? And again, we're going to the second point, is it done well? What's the right process, tools, and technique used? And after that, there's no way you need to look at the engineering of the system itself. So again, a personal view. But these things are feasible, but again, it's not something that's easy to do. Finally, biodigital convergence, and I have to go maybe a bit faster on that. It's another IT-enabled, again, area where this time it's IT and the life science. So convergence of engineering, nanotech, biotech, information technology, and cognitive science, a concept that was, again, 20 years old, but took a lot of speed. And it's a very wide area. What you see there in this map is, again, all the different science, technology contributed to the era of biodigital convergence. And on the right-hand side, you have the IT area, but you have a lot of other area. And an example, again, of biodigital convergence, but where you see simply not only IT contributed, is how cheap it is now to simply decode a human genome, but it's only a part of nature. It went down very fast, and faster than, again, Moore's law could have been contributed because new technology, new ways of decoding were enabled by this computational power and other progress. Proteins, very complex proteins. We have a lot of them in our bodies, synthesized, again, from the genome, but the synthesis is done like a 4D printer. It's a strand that's decoded, and then its protein will fold. If there are some errors, some change, the folding may be different. And the shape of those proteins can make a very big difference between a healthy individual and an individual that sometimes could not live anymore. So predicting the final shape of a protein is not easy. Talking a very long string, very complex computation, And what you see there is contribution to AI to be able to do that. Convergence again. And what you have there is the impact in different area of biodigital convergence. I'll zoom on one point there, the exoskeleton. We talk about cyborg, but essentially human augmentation, exoskeleton mean also restoring functions that have been lost. And as you can see there in this diagram, we're talking again, those kind of prostheses are cyber-physical system, IoT-based, with, again, sensor, actuator, and control unit. And again, the impact on society of all those different enabled technology. So to conclude, and I'm getting close to the end of my time, first, stakeholder of IT standardization nowadays include all those non-IT sectors. And for some area of standardization, like IoT, the most important stakeholder are these sectors. And again, this is a rough visualization of our GTC1 map into those areas, whose application sector facing mostly and whose IT sector, more traditional. And it can be, again, more refined, and I'll have a translation there for some of that when you look at different committees. There was an evolution where many, again, committees become more focused in some areas more than others. And an illustration, again, when you look at a smart grid about all those technologies that are coming back, those that I put as very horizontal. Now, this means, again, that there are some standards that are done, those reference architecture that will be invoked by, again, standards that are on higher level that are sector dependent. And again, a reference architecture, you mean is, again, an higher level architecture that's used to do a more specific one. And these reference architecture at the horizontal level exist, and there are some of them that exist or are being elaborated in those sectors there. Now, more cooperative and multidisciplinary work. You have the IEC that pushed that very aggressively in their system approach. And again, the reason why it's done is the same one. More complex environment need more cooperative work, different way to do standardization than it's the silo we had in the past. Now, I have to be careful, it's not new. There were some TC that had very complex work and were applying a lot of system concept in the past. But you have specialized system committees that have been created by the IEC, and you can see the last entry that was created 2 weeks ago on biodigital convergence. Now, we need to ensure trust, again, so we need standards that could be used in the engineering, not only in the engineering, but also because we need to have verified trust, it's conformity assessment. This is the term that's used in the ISO and the IEC. And I'll finish with this. Thank you very much for your attention.